Hello and welcome back to Functional Analysis. And as always, I want to thank all the nice people that support this channel on Steady or PayPal. In today's part 19, we will go back and prove Hölder's inequality. There are a lot of different inequalities named after Hölder, and indeed they are all related, but here we look at the simplest one. It's the one that holds in Fn and for p greater than 1. For each such number p, there is a Hölder conjugate, which we call p prime. The definition is what you should really memorize. The reciprocals should add to 1. This is an important relation because every time we use p prime, this is what we mean. Instead of p prime, a lot of people just use q. However, here I want to use q as another variable to tell you again what the p norm was. Or today I would better say the q norm of a vector x. It's defined by the sum over the entries in the absolute value to the power q. And then we take the qth root of the whole thing. And this is what we do for all q between 1 and infinity, including 1. Now Hölder's inequality will connect the p norm, the p prime norm, and the 1 norm. Indeed, it's one nice short formula you always should remember. I will now use a possibly strange notation to help you to remember the important inequality. Putting two vectors together just denotes a new vector which has the product in the components. So x2, y2 in the second component and xn times yn in the last component. Then for all vectors x and y, we have that the 1 norm of the vector xy is less or equal than the p norm of x times the p prime norm of y. And that's what we call Hölder's inequality. Often you see it written with the sums, but I think it's better to write it immediately in this way. On the one hand, it's easier to remember, and on the other hand, we will generalize the whole thing later on. Indeed, there we will have the whole inequality for functions defined on an abstract measure space. However, that's not what we do today. Today we prove it for vectors in Fn. In order to prove Hölder's inequality, we first need another inequality, which is known as Young's inequality. In fact, this one is very simple. We just look at positive numbers ab, and then we conclude that the product of ab is always less or equal than the following sum. So what you should see here is that p greater than 1 goes in and the Hölder conjugate. So as before, you can choose p greater 1 as you want, but then p prime is fixed. For example, for p equals to 2, we have p prime equals to 2. However, in this case, you already know that the inequality here is correct. So please check that, but for all other cases, we have to write down a proof. What we can use here is that the common exponential function is a so-called convex function. This means that when you look at the graph, then you can choose any 2 points as you want. The direct connection would be always above the graph. This property is called convex because the red line is the convex combination of the 2 points. Therefore, we can easily put that into a formula when we call the function just f. Now, by denoting the 2 points by x and y, we can form a convex combination of x and y and put that into the function f, which means we get out the blue line here. Please recall, a convex combination is just a special linear combination where we only have one lambda, which comes from the interval 0 to 1. Now with the red line, we also get a convex combination with the images, which means we have here instead of x and y, just f of x and f of y. Therefore, being always above the blue graph means we have here our inequality, which we now want to use for some special numbers. Lambda should be 1 over p, and then 1 minus lambda should be 1 over p prime. Maybe that's not so clear, but for x I want to put in the natural logarithm of a to the power p. And a similar thing for y, but now with b and p prime. Of course, this all fits together because by applying the logarithm rules, we can bring this power in front where it cancels out. Hence, on the left hand side, we have the 2 logarithms in the function f. Now using the next logarithm rule and the fact that the exponential function is the inverse function of the logarithm, we have just ab on the left hand side. And now you see the idea of the whole proof. We want to show this one, and we are already finished with the left part. Regarding the right hand side, we just put in all the numbers we already know. Now this looks more complicated than it really is, because we have again the inverse function of the logarithm here. Hence this all vanishes, and what remains is what we wanted to show. So Young's inequality is correct, and we can use it to prove Hölder's inequality. Starting with the proof, let's first consider the simplest case. What I mean by that is that we look what happens when x is the zero vector or y is the zero vector. But of course this is not a problem for us, because by the definition of all the norms here, we have that the left hand side is 0 and the right hand side is 0, so the inequality is fulfilled. Therefore, for the second case, we can divide and bring everything to the left hand side. Of course, now we want to bring this inside the norm and divide x by its p norm and y by its p prime norm. However, since I use this strange notation here, I bring in now the whole sum of the one norm. Here we have it, and we can pull in the norm into the sum and then into the absolute value. And there you should see now that we have two positive numbers, which we could call a and b, and then apply Young's inequality inside the sum. So at this point we get the inequality sign in. Okay, the first term is 1 over p times xj to the power p divided by the p norm to the power p. The second term looks similar, and I already distributed the sum over both parts. So here we just have p prime and j instead of x. However, that's not so important. The important thing you should see is what we have in the numerator together with the sum is the same as the denominator. And the same in the second part. Hence the only things that remain is 1 over p here and 1 over p prime here. And by the definition of the Hölder conjugate, this is simply 1. And with this we have proven Hölder's inequality, because you can bring this one on the right hand side again if you want. So you see, the proof was not so hard, but we will need Hölder's inequality to prove another inequality. And this one will be the so-called Minkowski inequality. Essentially it's just the triangle inequality for our LP space. Therefore, I hope I see you in the next video. Thanks for listening and see you then. Bye!